Hello, everyone. My name is Xiaoyu Zhang. I'm a postdoc fellow from ETH AI Center. Today, I will present our work, Slicing, Chatting, and Refining, a concept-based approach for machine learning model validation with ConceptSlicer. This is my second internship project with Bosch Research and Technology Center, and also a collaborative project with George Wenbing Liang Liu from Bosch Research, my postdoc advisor Marimaya from ETH Zurich, and my PhD advisor Kuang Lu from UC Davis. Now let me start introducing our work. As machine learning gains wider adoption in real-world applications, such as smart transportation, medical image processing, smart manufacturing, e-commerce, online education, and space exploration, the validation of machine learning models becomes fundamental for its productization, particularly in safety-critical applications. Recently, data slice finding, which means identifying human interpretable and actionable data subgroups with metadata, has emerged as a popular method for validating machine learning models. However, achieving transparency and interpretability in slice finding often requires additional metadata or cross-model embeddings. When it comes to the model optimization stage, data augmentation is a popular approach to address model biases and performance issues. However, collecting the right data to address a model problem remains a costly and time-consuming process. To address these challenges, we propose ConceptSlicer, an integrated workflow that facilitates the slicing of computer vision models using visual concept. Our workflow takes validation dataset as input. To get rid of the dependency on additional metadata or cross-model embeddings, we identify interpretable visual concepts from the images using a self-supervised semantic segmentation model, and use them as the metadata for the slice finding algorithm. Together with the model performance results on each image, we find underperforming data slices. For this model, we use a breadth-first slice finding algorithm. Afterwards, we support users to interactively select the most critical slices for further analysis. While interpretable visual concepts in the last step can highlight the key element of each slice, users may still need further inspections to understand the theme of the slice and the reason for the model failure. We facilitate this process by employing ChatGPT to generate scenario descriptions for a given slice. The input prompt for ChatGPT is constructed by merging the class name and concept labels with a predefined template. Afterwards, ChatGPT would generate multiple scenario descriptions for our users to select interactively. We obtain unified embeddings for both the images within the slice and the scenario descriptions using OpenClip, an open source implementation of Clip, and then calculate their semantic similarity to retrieve supplementary images from an additional image dataset. Finally, we can retrain the model with the augmented data. ConceptSlicer is an iterative workflow, so users can use our solution to optimize their model for multiple runs until they are satisfied with the results. We developed a novel visual analytics system to implement this workflow. In this first use case, we will demonstrate how our system can help identify various issues in the object detection model. In particular, how it can help alleviate model defects caused by complicated cases involving spear-speech correlations and object overlapping for the class horse. After importing the model performance data into the system, we can see that the model has the worst performance on slice 1, defined by 2 absent concepts and a present concept. By checking the suggested concept details and browse the sample images, we find that most images in the slides depicts people riding horses on the ground without grass. So there might be a spurious correlation between horse and grass. We can also see that in most of such scenarios, people overlap with horses. As a result, the detection boxes unavoidably include both horse and human torsos, which might cause confusion for the model. Based on such observation, we can instruct ConceptSlicer to request for scenario descriptions from ChatGPT for this slice. More specifically, ChatGPT generates scenarios with horses, but without grass. We can select the sentences with the most interesting scenarios that align with the prompt and use OpenClip to fetch the images. Then we can browse the retrieved images, remove the irrelevant ones, and export such kind of supplementary images for dataset augmentation and model fine-tuning. Afterwards, we can train a new object detection model based on the augmented dataset. We invited 8 domain experts or practitioners to evaluate this case with ConceptSlicer. And we observed that they employed primarily 3 different strategies to select supplementary images and enhance the dataset. With the exception of expert 1, all other experts were successful in improving the performance of the data slices they chose to optimize. As an additional use case, we can illustrate the use of ConceptSlicer to address poor model performance caused by the missing of critical concept. When using ConceptSlicer to provide the car class, we noticed that the model's overall performance is not acceptable. By checking the size browser, we find that the underperforming sizes were constantly associated with the absence of the same concept, 440. The vision language model suggests these concepts may correspond to car, truck, or TV monitor. Why does the absence of this particular concept have a recurring impact on model performance? We may find the answer from the concept view. This concept has a significant relevance to a critical component of the car, the windows. In the majority of the slices, where concept 440 was absent, the windows were either not visible due to the viewing angle or because the cars were too small to discern the windows. To mitigate this issue, we can prompt ChatGPT to describe scenarios that involve cars, but car windows are not visible. Here we get some very creative scenario descriptions, and we can select some of them. Now we instruct ConceptSlicer to retrieve supplementary images based on our selection, and which will help increase the dataset coverage and improve the model performance after retraining. To wrap up, we developed ConceptSlicer, a workflow and corresponding system to streamline the process of validating computer vision model. Our quantitative and qualitative evaluation with human experts emphasize the effectiveness of our system in the sphere of model validation and evaluation. It also showcased the potential of systems like ours to harness the power of large language models and showcase a promising future for machine learning model validation. That concludes my presentation today. For more details, please refer to our paper. Thanks for your attention.